Hello, this is Mr. White, and this video is on finding the area of a planar region, part 2. And here's the one exercise we'll focus on for this video. We will be using the limit and summation process to find the area bounded by the x-axis and this curve, and on this interval of x values. So let's start by just drawing a sketch so we have a good visual of what we're trying to do here. And as far as drawing that parabola goes, it doesn't have to be super detailed, but let's at least do this. Let's note that since there's no constant term at the end of that quadratic, we can factor this very easily into x times 2x minus 5. And if I then set that equal to 0, I will get my two x-intercepts without much trouble. So x equals 0 and x equals 5/2 are the two x-intercepts. So if I put some numbers here, 1, 2, 3, 4, 5, 6, 7. Want to make sure we at least got to 7. I know that this parabola is going to cross at x equals 0 and 5/2, or 2.5. And I know that this is an upward facing or smiling parabola because of the positive coefficient for the quadratic term. All right, so if the vertex is somewhere around here at x is 1 1/4, this parabola would look something kind of like that. Not the best picture, but good enough for what we're doing. And again, we really just want the area underneath that curve and above the x-axis on the interval from 3 to 7. So we're looking for this area in here. Now notice that these instructions didn't tell us whether to use a left sum, right sum, upper sum, lower sum. We really have our choice. And remember, it really doesn't matter which one we choose, because when we take the limit of the left sum, right sum, upper sum, lower sum, remember all of them will have the same limit. They all will give us the area that we're looking for. So we'll just use whatever sum is easiest. And you may recall from our recent work that we tend to find the right sum a little bit easier than the left sum. Remember, it has to do with the right sum tends to give us sigma I, whereas the left sum tends to give us sigma I minus 1. I'll ask you to consult the earlier video or your notes for why that is. But that's why I'm drawing some right sum rectangles. And they're right sum rectangles because it's the right upper corner of the rectangle that lies on the curve. So I'll just do a dot, dot, dot here. We'll do our last right sum rectangle here. And I'll go ahead and do one right before it, the one right preceding it. And if we claim that there are n rectangles crammed underneath this curve here, we then look at the total interval, the total width of the interval from 3 to 7, and we say, oh, that's a width of 4. So a width of 4, a total interval of 4 divided by n rectangles tells us that each of those individual rectangles, where we are assuming that they're evenly width, each of those rectangles is going to have a width of 4 over n. So you should recall that that will definitely play into our sigma setup in a moment. But before we get to the sigma, let's figure out the x values for each of those rectangles, which we know we also need to know. Let's look at rectangle number 1 here, and its relevant x value corresponds to this right point, correct? So this x value, we'll call that x subscript 1. That's going to equal 3 plus the width of one rectangle. And we said that the width of one rectangle would be 4 over n. For emphasis, we'll put a 1 there. So let's move this over here and look at the next x value for rectangle number 2. For rectangle number 2, we're focusing on that right corner, and therefore this x value, and we'll say that x subscript 2 is going to equal 3 plus the width of 2 rectangles. So 4 over n being the width of one rectangle times 2 rectangles. And you've seen this before, you get the idea. We could even leapfrog all the way to the end. That nth rectangle, rectangle number n, looking at that point and the corresponding x value, we could even see that it fits within the pattern as well. That x subscript n for the nth rectangle would be 3 plus 4 over n times n. And of course, we see in that case that that simplifies to just 3 plus 4, which is 7, which is appropriate for this point. So here, now that we identify the pattern, here's what we're really interested in. I'm just going to put a line here to represent some generic ith rectangle. And we'll say that its corresponding ith x term will be x subscript I equals 3 plus 4 over n times I. And that will be our generic ith x value. So pause if you need to, replay if you need to. I'm going to erase some of this just to clear up some space here. Okay, so our generic ith rectangle has this x value. Let's scroll up here, and I'll just represent that in our picture just somewhere in the middle there. Okay. So let's now start adding up all these rectangles. We'll go straight to sigma notation here, and we'll say sigma of base times the height of the rectangle, where we agreed earlier that the base for every rectangle is 4 over n. And the height is going to be the y value at each corresponding x value. So, in other words, f of x subscript I. Where we go from the first rectangle, I equals 1, all the way up to the nth rectangle. Now, what we have represented here is the right sum, again, so we could call that s subscript right. But in the end, we were told to just find the area. We were not so much concerned about just getting the right sum precisely as we are getting the area under that curve. So let's not worry about it being the right sum. Let's go ahead and take the limit as the number of rectangles goes to infinity. And that entire expression will give us the exact area under that curve. So let's proceed. Need a little more room even here. Okay, so for figuring out what to put for f of x sub I, we will use both our f of x, I know it says y up here, but we'll think of it as f of x, and we'll use the x sub I definition down here. And that will give us 2, and that's where the x is going to go. I'm just going to finish the blanks here. 2 blank squared minus 5 times blank. Again, what I'm doing here is I'm writing the expression for f of x sub I. And let's fill in the blanks with 3 plus 4i over n. Both places, 3 plus 4i over n. That represents the height of each rectangle. We'll go ahead and multiply it times the base here, 4 over n, being sure to include parentheses as appropriate, or brackets as appropriate. And we'll put the summation and the limit there. So this would be a point where if you missed anything along the way, pause, back up, think about it if you need to. Make sure you understand how we got to this point, because it's pretty much algebra from here. And therefore, since we've been getting used to this lately, I'm going to speed it up a little bit here. So let's distribute this out. 3 plus 4i over n times another 3 plus 4i over n will give us 9 plus 24i over n plus 16i squared over n squared. And if I go ahead and distribute the 2 here, that will give me 18 plus 48i over n plus 32i squared over n squared. I'm going to go on to the next term, this here, being sure to distribute the negative. So that's going to be minus 15 and then minus 20i over n. Okay, with the rest of the decorations, of course. And I'm sure I've said in class that I am okay if you just put lim and sigma. As long as you put something there, I'm okay with that, even if you don't put all the extra details. Just put something to remind yourself that we do have to add these up and then take the limit. Okay, so let's, before we distribute the 4 over n, let's combine some like terms here. 18 and minus 15 will give us 3. 48i over n minus 20i over n will give us plus 28i over n. And then finally, the 32i squared over n squared. Plus 32i squared over n squared. I'm going to recall my goal to just get sigma I squared, sigma constant. And let's go ahead and jump to that point. So if I distribute 4 over n times 3, I could get 12 over n. I'm going to take it outside a sigma 1. 4 over n times 28 over n is going to give us 112 over n squared. And that I is still inside the sigma, so sigma I. And finally, 4 over n times 32 over n squared. That'll give us 128 over n cubed, and then sigma I squared. And let's not forget that we will ultimately take the limit of all of those sigmas. We'll bring up the 3 relevant summation formulas and substitute those in. This sigma here will give us just an n, according to this formula. This sigma here will give us the n times n plus 1 over 2. And this sigma will give us this longer formula, n plus 1, 2n plus 1 all over 6. And I'll fill in the rest of that. And this is where we can take a little bit of a shortcut. If you remember that in the end we are interested in the exact area, we're not interested in plugging in values as we've been asked for in the past, like n equals 10 rectangles or 100 or 1,000 rectangles. We don't need to do all that. We're going to go ahead and take the limit. So let's take advantage of that. Let's recall that for limits as n goes to infinity, that's where we look at expressions like that and say, oh, the plus 1 is pretty negligible. So we cross out the plus 1. Likewise over here, that's where we say the plus 1 in both factors is negligible. And obviously at this point, do whatever you need to on paper to ensure that you're being careful and getting everything accounted for. But this is how I would do it. N over n gives me just 12. I see here that since I've crossed out the plus 1 right there, I see that now I've got n squared and an n squared here. And those will divide each other out or cancel each other out. And I'll be left with 112 over 2. And over here, what I've got left is 2n cubed over this n cubed. So I've got a 2 left over a 6. And then there's that 128 there in front still. So 128 plus, and again, I've taken the limit here. Assuming n going to infinity and doing all that canceling, that was the limit, so I don't write limit anymore. Okay, the 2 6 here, that reduces to a 1/3, so I can cross those out and put a 128 over 3 there. Okay, I encourage you to try out your mental math. 112 over 2, that's 56. 56 plus 12, that gives us 68. I see that I have a 68 plus 128 over 3. We're going to do our common denominator, right? So 3 times 68 gives us 204. And 204 plus 128 here, that will give us 332 over 3. And that does not reduce, so I put a box around it. And given that that's an area under the curve, it may feel like you maybe would prefer a decimal answer. I don't mind this answer at all, but if you do, consider that 333 over 3 would give us 111. So we just subtract 1/3 from 111, and we'll get 110.6 repeating. And don't even need a calculator for that. That is our final answer. Last thing we'll do is verify by calculator. I get the equation typed in. I'm interested in the interval from 3 to 7, so I know that zoom standard, zoom number 6, will do the trick. So I just press number 6 on the keypad. It's not the best viewing settings for seeing this graph, but it'll do. I'm just interested in the area under the curve, so I go to Second, Calc. I'm going to press number 7 on the keypad. And the lower limit is 3, so I enter 3. And then the upper limit is 7, so I enter 7. And I see the shading. Again, I don't see all the shading. It goes off the top of the screen, but at least I see the number that I'm interested in down here. I see that the answer, 110.6 repeating, matches ours.